Okay, so we're on question 4. A student investigated the change in temperature when oils of different specific heat capacities were heated. She sets up the apparatus shown in figure 5. Here we are. So, specific heat capacity. If you want to take a hot water bottle to bed with you, do you fill it with water at 100 degrees Celsius or oil at 100 degrees Celsius? The same quantities. Well, it turns out the water would keep you warm for twice as long because different materials store different amounts of heat energy in terms of the joules of energy required to heat them up to that temperature. So Alan Partridge has annoyed this man and he wants to beat him up. So he's going to use the apple pie to defend himself.
The temperature inside this apple turner is 1000 degrees. If I squeeze it, a jet of molten Bramley apple is going to squirt out. Could go your way, could go mine. Either way, one of us is going down.
Alan, I've just come to make peace.
Now the thing here is that at 1000 degrees Celsius
Shake hands, you know?
is not the thing that's going to cause the burns. It's the amount of heat energy stored. You could get hit by a spark from a sparkler, which is thousands of degrees Celsius. Right. If your liquid-based apple bramble thingy job has been heated for 8 minutes, you've stored a lot of thermal energy in that in the form of joules of thermal energy, and that's what's going to burn you for the same temperature rise for the same amount of stuff. So that's what this is all about. I have some good YouTube videos on this worth checking out, very popular ones as well. But without further ado, let's carry on with this question. So, this is the method used. Put 25 grams of oil into a boiling tube. Pour 100 ml of water into a beaker and heat it with a Bunsen burner. When the water is boiling, put the boiling tube in the beaker. When the temperature of the oil reaches 30 degrees Celsius, heat for a further 30 seconds and record the rise in temperature. Repeat with different oils. Repeat the whole investigation. Okay. Name 2 pieces of apparatus the student used that are not shown in figure 5. Okay, so let's have a little look. It does say somewhere that you have to time it for a further 30 seconds. So we'll definitely need a stopwatch. Right. And then thinking about it a bit further, I mean, if you're measuring 100 ml, what are you doing that with? With a measuring cylinder, that would make sense. There isn't a measuring cylinder shown here, so I think that would get us the marks for that. Okay, so question 4.2. What are the independent and dependent variables in the student's investigation? Okay, so what have we got here? Independent and dependent variables. Okay. So, independent is always the thing you change. The one thing you change. And the dependent variable is the thing you measure. Right? Because usually you're going to put a graph like this. You'll put the thing that depends on the thing that is being changed. So, if, like for instance, I decided not to eat for 4 days, you could count the number of days, 1, 2, 3, 4, and you could look at my weight over that time, and you could see how my weight depended on the number of days I didn't eat. Hopefully you'd see it drop like that. Not that I'm suggesting you do that. So what was the independent variable? What were we changing, right? So we were doing this with different types of oil, so that has to be our independent variable, the type of oil. And what were we seeing? How things change? We saw that we were changing the types of oil, but we were recording the rise in temperature. So we wanted to see how the rise in temperature. Depended on the type of oil, right? So it would be rise in temperature. I should really write the whole thing. Rise in temperature. Okay. Give 2 safety precautions the student should have taken. Let's have a look at the actual apparatus. So we're dealing with a flame, potentially some hot oil. Some safety goggles might not be a bad idea. You're also dealing with a flame, so I suppose tying back long hair could be an option. You should be careful to avoid, because you've got boiling water there as well, you'd have to be careful to avoid spills, so not sitting whilst doing the experiment would be a good one as well. So I'm going to go for safety goggles. Safety with a white safety goggles. And I would say standing to avoid spills. I should really put hot spills. You can imagine if you're at a bench and you've got
a tripod with some hot water in here boiling away, the flame here, and you're sitting down here, splash. Doesn't really bear thinking about, does it, guys? Or ladies, anyone.
Right, suggest one improvement to the student's method. Well, she has said repeat the investigation. Okay. 25 grams of oil into the boiling tube. Heat for a further 30 seconds. Okay. So, when you have... Oh, they haven't put a thermometer in here either. I just noticed that as well. You need a thermometer in here. So you're taking readings off this thermometer, right? You're going to take some readings off this thermometer. And you're going to heat this oil just for 30 seconds. If the thermometer temperature goes from, say, here to here, whenever you take a reading from any device, right, you get at eye level and you make sure you read it at eye level, so you're not making parallax errors, but you'll never read it 100% accurately. So if the temperature change is just, say, 3 degrees Celsius, well, every time you take a reading off a thermometer, you're going to have plus or minus of maybe a whole degree Celsius on that, right? So if you can make it so that the change in temperature is larger, then your error accounts for a smaller percentage of it, right? If you're measuring something that is 1 millimeter high with a ruler like this, then it's going to be quite difficult to do it, right? And your error is going to be quite large compared to what you're measuring. If you're measuring something that's much taller, like this mug, right, then your error, this is about 10 centimeters high. 1 millimeter out of 10 centimeters is a very small amount. It's 1%. Yeah, it's 1%. So that's what this is talking about. So I think we could try heating it for longer, and that way we'd get a larger temperature. So our larger temperature change. So suggest one improvement. I would say heat for 1 min to achieve a larger temperature rise. 3 dots means therefore less error due to reading thermometer or temperature. Always go for the easiest spelling.
Crash! Bang! Wallop!
Right. Table 1 shows the student's results. Type of oil. There are 3 different types of oil. Oh, no, sorry. There are type of oil here. And then we have 3 different goes. They repeated the experiment 3 times. So we've got castor oil, linseed oil, mineral oil, olive oil, sesame oil. Okay. And various readings. And they wanted to calculate, calculate the mean temperature rise for olive oil. Give your answer to 2 significant figures. So, answer has to be 2 significant figures. We're doing the mean temperature rise for olive oil. So let's just quickly check, because they usually stick in a dodgy result. 17, 17 and 18. Right. So there's no anomalous results here. If you had, say, 17, 17 and 30, I would eliminate 30, add up 17 and 17 and divide by 2 and get 17, and that would be perfect. Here, though, there's no anomalous
results, so it's simply going to be a case of 17 plus 17 plus 18, all of which, if you do it on calculator in brackets, divided by 3. So, quickly I'm going to do that. 17 plus 17 plus 18, divided by 3, 17.333 recurring. Right, that goes on forever. They say to 2 significant figures. two significant figures would just be 1, 2. So I'm rounding down. I'm just going to say the mean temperature rise is 17
degrees Celsius. Okay, so let's look at the next question. The mean change in temperature of castor oil is 20 degrees Celsius. The specific heat capacity of castor oil is 1,800 joules per kilogram per degree Celsius. The mass of oil used is 0.025 kilograms. Calculate the change in thermal energy of the castor oil the student used. Use the correct equation from the physics sheet. Select the correct unit from the box. 3 marks. Right, a couple of important things to point out. 3 marks. Worth doing. Use the equation sheet. Here's the equation sheet right here, so we can look at it. Things to point out. This is in kilograms, but this is the only time we don't need to change it. It's the only SI unit that's got a prefix is mass in kilograms, so we don't need to change that. So I'll follow the instructions. I will use the correct equation from the physics sheet first. So let's go looking. I'm supposed to calculate change in thermal energy. I have change in temperature, I have specific heat capacity, I have mass. So let's have a little look. Velocities, acceleration, no. Elastic potential energy, no. Change in thermal energy, mass, specific heat capacity, change in temperature. Bingo, that is the one. Okay, so like I said, first things first, take the formula. E equals mc delta theta, right? Once you've got your formula, that's probably going to be worth a mark just for showing you know which formula to use. Go through and substitute your numbers in first, right? So, do I know the energy? No, because that's what I'm being asked to calculate. Do I know the mass?
Yes, it's 0.025 times by C. What does that stand for? Specific heat capacity. Well, I've been given that, 1,800, times by delta theta. What's that? Change in temperature. Change in temperature, the mean change in temperature was 20 degrees Celsius. Right, so I just have to multiply these 3 numbers together. 0.025 times 1800 times 20. 900. Right, so it's 900. And then I have to put the correct unit, and the unit is joules. Energy is
measured in joules. Okay, thanks for watching. I hope you found this useful. Please comment, like, subscribe, and share.
Crash! Bang! Wallop! What a video!